Good morning, everybody. Hope you're all doing well. Morning, morning. Good to be with all of you. So as I always know, people are trickling in right now. But that being said, let's get started. So today we're talking all about humidity. So last time we began talking about water in the atmosphere when we were talking about this concept called latent heat. Well, today we're going to take it a step further, and we're actually going to talk about the water itself and how it greatly influences the atmosphere. So that being said, let's start with a nice little up question, and I will paste the link here in chat. But if you've ever gone outside in the morning, you've probably noticed, even on a relatively not super cold morning, that there's dew on the ground. There's dew on the grass, there's dew on any surfaces. If you try to sit on a bench, it's covered with dew. There may even be some fog. But why is that? Why is there dew on the ground in the morning? And why does it go away in the afternoon? So take a moment. For those of you who just walked in, I will paste this link in chat a few more times. And as always, I'm just looking for your thoughts. I'm not looking for the great American novel or a professor. I just want to know what your thoughts are. All right, a few more people have come in, so let me paste the link again. Welcome, everybody. Good morning. Thank you for those of you who have your webcams on. I'm just always so happy to see faces. Alrighty, I was just about to do that. Let me post the link one more time. And then here we go. Absolutely. I'll give you a few more minutes to noodle this and get your brains warmed up, and then we will jump in and talk about it. Let me pull up the question in my other browser. See where people are at. Okay, it looks like almost everybody has commented. I know a few people still need to, so I'll give a few more moments for that. see. Let's take one more minute. I'm going to start looking at the responses. Mhm.
Professor,
Oh, yeah.
could you link the Google Doc again, please?
Alrighty, here we go. Oh, whoops, sorry. Mhm. Oh no, my internet browser just crashed. Weird. Let's see if I can get it back up.
What up, blood?
Who was that? Did we just get a Zoom bomber? I think that was a Zoom bomber. Kind of sad people who have nothing better in their lives to do than to go around and troll classes. Okay. Well, it looks like most people have responded. So now that most people have responded, let me share. Agreed, Jerome. Okay. So let's take a look and see sort of what the general consensus was of people. Whoops, let's scroll down past the name. Oh, I can just click on question. And here we go. Water vapor in the cold air. As temperature rises, the water starts to evaporate. The temperature outside is cooling down right before the sun comes up and warms it up, so they evaporate. Dew forms when you have cold temperatures. It disappears when the sun comes out. Condensation and then evaporating from the sunlight. That looks good. Unsure. Thank you for being honest. I felt the temperature in the night drops to the point where water vapor coming in contact with the cold grass enables condensation. I agree with that. Overnight dew is formed from objects cooling down. When the sun isn't at its peak or heading to its peak, where it starts to get warm. So the dew is on the floor, hasn't really gone because of the temperature not being warm enough as it is in the afternoon. Let me just kind of scroll through here real quick and see what a few other people have said. The water is evaporated by afternoon, condensed during the night, evaporated by the afternoon. Something to do with vapor from the atmosphere. Condensation and evaporation, something related to condensation. By the time the afternoon hits, the water has evaporated. So the general consensus that I'm seeing here, is it has something to do with the idea that at night the temperature gets cold. That causes water to condense. And then as the sun comes up and as temperatures rise, that same water evaporates. Yeah, that's pretty much the that's pretty much the quick and dirty of it. So let's actually talk about what's going on there. Let's actually talk about what's going on there. Let me switch back over to ye olde PowerPoint presentation, and let's do it. So we talked about this a little bit at the end of class last time, so I'm not going to go super into detail this time around. But if you remember from last time when we talked about the water cycle, one of the concepts that we talked about was sort of the basic, what I call the TLDR version of it, which is during a hot sunny day, the sun heats up the ocean. That causes the water to evaporate. That evaporated water then rises in the atmosphere, cools and condenses to clouds. As this continues, those clouds get bigger and bigger and bigger, and they begin moving their way inland. Eventually, they get so big that they rain out as precipitation, either in the form of rain or snow or sleet or hail or any of those things. That precipitation then collects in lakes, channels, and streams and runs back off into the ocean. There's a lot of other potential legs in the water cycle. Some of the water can actually seep down into the ground and become a part of what's called an aquifer. Other bits of water can be dammed into reservoirs. I damn you to that reservoir. Others can end up becoming parts of glaciers and staying permanent ice, essentially. Others get consumed by either trees, plants, vegetation, or even humans. And then we all expel water as well. I don't want to go into the quick and dirty of that. But those are all alternative paths on the water cycle. But the real thing I want you to know right now are the concepts of evaporation, condensation, and precipitation. Because those are what we're going to talk about today, next Tuesday, and next Thursday when we get into precipitation processes and how they work. All right. So just a few key terms that you need to know before we jump into today's content. Evaporation, that is a phase change moving up a phase. That is an upward movement in a phase where water changes from a liquid to a gas. Condensation is the exact opposite. When water changes from a gas to a liquid. And then finally, precipitation is when liquid water falls and hits the ground. So it falls from the sky, makes it down to the ground. So evaporation is that process of going from a liquid to a gas. Condensation is that process of going from a gas to a liquid. And precipitation is when this water falls from the sky. Now imagine, if you will, a glass filled with water. A glass filled with water. I have a can with some bubbly on it. Or even what you can do is take a little bit of it and spill it onto your table or onto a surface of something. Well, if we were to actually zoom in and take a look at what was happening on a molecular level, there's actually some pretty crazy things happening to this water. So here's what's actually happening. If you zoom in to the surface of that water, so that's that boundary between the water and the air above it, and you actually looked at a molecular level, what you would see is you would see this process where water molecules, those are these little Mickey Mouse looking things, are actually either, let me pull up my laser pointer, are either escaping from the surface of the water, that's evaporation, or returning to the surface of the water, that's condensation. So at the surface of any body of water, either the glass of water you have next to you or other beverage you have next to you, water that you spilled on a table, or any surface of water, a lake, a stream, anything, that boundary between water and air, there's actually water molecules that are actively escaping and actively returning to the water. Typically, more are escaping than returning. Typically, more are escaping than returning. We call this net evaporation. So think about it. A moment ago, I actually poured a little puddle of water on my desk. Let's assume that I committed to not wiping this up. I told my wife, please don't wipe this up either. Neither one of us is going to wipe it up. Instead, we just let it sit here. What would eventually happen to this little puddle of water? All right, I got some people in chat talking. Let's see what they say. Poof, gone, evaporate, sayonara. Yep, exactly. What would happen is over time, because more water molecules are escaping than returning, over time, what's actually going to occur is the puddle's going to get smaller and smaller and smaller and eventually gone. This is what's typically happening in the lower atmosphere. Down here in the lower atmosphere, we are typically experiencing net evaporation, meaning that down here, more water vapor is evaporating than condensing. That's why we don't see puddles of water sporadically forming all around us. So it's because of that concept of net evaporation that it stays relatively dry down here. That's a good thing. I don't know about you, but I don't want water forming all over my body nonstop. That wouldn't be that fun. Well, here's a little known fact about water vapor molecules. Each water vapor molecule exerts has a mass. It's matter, it's made up of something, and therefore it has mass. Well, something that has mass exerts a weight. I'll say that again. Something that has a mass exerts a weight. Something that has mass exerts a weight. Well, what actually happens is, as water evaporates, that now means there is more and more and more water in the atmosphere. So what's happening to the atmosphere as more and more water gets put into it? What's happening to the weight of the atmosphere? It increases. Yeah, it gets heavier. It increases, it gets heavier. It gets heavier. I love it. Yes. It gets heavier. That's exactly what happens. We actually have a term for this. So the weight of the air due to water. So if we were to take just water out of the air and just measure that pressure, which pressure is just weight, we would call it vapor pressure. So the pressure in the atmosphere due to water vapor is what we call vapor pressure. I'll say that one more time. The pressure of the atmosphere due to water vapor is called vapor pressure. It's called vapor pressure. All right. Now think about this. Think of each water molecule as a book. Think of each water molecule as a book. And let's imagine that, I'm going to pick somebody at random because I'm mean. Nope. Sorry. Let's imagine that Connor is the atmosphere. So let's imagine that Connor's the atmosphere. And let's imagine that water molecules are like books. And let's say we were in a classroom and I had Connor walk around, and each one of you, as he passed, you would put your book onto a pile that he's holding on to. As he's walking around and every one of you putting a book onto his pile, what's happening to that pile?
It's getting heavier.
It's getting heavier and heavier and heavier. Exactly. Well, the same thing is happening to the air above a surface of water. That air above a surface of water is getting heavier and heavier and heavier. Now, let's suppose that we were to put a lid on top of this glass, or we were to cover our little puddle or whatever. Well, what's going to happen is at some point, the more water molecules that evaporate, the heavier that air above the surface of water becomes. The more people that put books on Connor's pile, the heavier the pile becomes. Well, eventually, the pile becomes so heavy, if people keep doing that and doing that and doing that, what's eventually going to happen to Connor?
I'm gonna collapse.
You're going to collapse. Yes. Connor is eventually going to reach a threshold where he can no longer hold on to any more books. If even one more person tries to put another book on his pile, Connor's going to scream, "Take that book off," or he's going to drop everything. Unfortunately, the atmosphere is not that cool. Well, I'm not saying that it'd be cool to collapse and spill a bunch of books, but what does happen is at some point, the atmosphere reaches a state where it cannot take any more water vapor. If even one more water vapor molecule is added, another one needs to condense. And that is what we call saturation. So just like at some point, Connor's going to reach a threshold where he can't hold on to any more books, the atmosphere eventually reaches a threshold where it can't take any more water vapor. At that point, any additional water vapor would be forced to condense right back down. This is what's called saturation. So I will talk a lot about saturation today. The idea of saturation, and I cannot believe I'm going to say this, I'll explain why this makes me cringe so much later. But the idea of saturation is just like at some point, Connor can't hold on to any more books. At some point, the atmosphere can't hold on to any more water. At that point, the atmosphere's relative humidity is 100%, meaning it is holding exactly as much water as it can. It can't hold another molecule. If it does, it'll drop it. Just like if you add one more book to Connor's pile, he would drop it. So the concept of saturation is just that. The idea is that this is rain, right? Actually, we're not quite to rain yet. What actually happens in this case is little water droplets begin to form, and they can oftentimes form as clouds or as fog. Believe it or not, the process of taking one of those tiny droplets and turning it to a raindrop is very, very complex. We're actually going to talk about it next week, though. So awesome question. Thank you for asking me that. Somebody asked me in chat, a private message, is that rain? So thank you for asking that, because that is a good jumping point into what we're going to talk about next week. So thank you. Okay. So in a saturated atmosphere, the atmosphere can't hold any more water. It has maxed out. It cannot hold any more water. So how does this relate to temperature? Well, when the air is hotter, what is going to be happening more? Which of those two things is going to happen more, evaporation or condensation? Exactly. Those who are speaking in chat, there's going to be more evaporation. Warmer air promotes more evaporation. So even if the air becomes heavier and heavier and heavier, there's enough energy in the air because it's so warm that it can just take on more water vapor and more water vapor and more water vapor, allowing for more moisture to be in the atmosphere. More evaporation is promoted, more condensation is demoted, not allowed. On the other hand, if the air is colder, you don't get as much evaporation and you get more condensation. In this case, there's less moisture that's possible in the atmosphere. So in short, this brings me to a statement that I am going to have a hard time sleeping tonight for saying it. I'm probably going to get fired if anybody hears me say this. You probably might want to report me to administration after I say this. I'm going to cringe for saying it. Warm air holds more water vapor than cold air. Warm air holds more water vapor than cold air. Now, why am I cringing? Why am I doing that? The reason why, and it's more a joke than anything. Nobody's going to fire me. All Met 10 teachers teach it the same way. But the reason why I want to be very careful with using that terminology is saying that air holds water is actually very bad terminology. Really what it's all about is it's about this balancing act between evaporation and condensation. When air is warmer, it's able to, or more evaporation is happening, more evaporation is able to happen. So warm air holds more water vapor. Because there's more evaporation, there's more water vapor in the atmosphere. On the other hand, when it's cold, you can't get as much evaporation and instead you get more condensation. So in that case, cold air holds less water vapor. Tying that all together, as temperature goes up, the amount of water vapor the air can hold also goes up. Now let me explain this in a little bit more scientific and a little bit more conscience cleaning way of explaining it. So who can remind me, a few minutes ago, I mentioned this thing called vapor pressure. What was vapor pressure again?
The weight of water in the air.
The weight of water in the air. So what would happen to vapor pressure if I put more water in the air? If I add more water vapor to the air, what's going to happen to vapor pressure?
Increases?
It's going to increase. Absolutely. Yeah. The more water vapor there is in the air, the higher the vapor. Sorry, I had to clear my throat there. The more water vapor in the air, the higher the vapor pressure. The less water vapor, the lower the vapor pressure. So basically, vapor pressure just tells us how much water vapor is in the air. It just tells us how much water vapor is in the air. But there's another term that I need to mention. So vapor pressure is simply determined by how much water vapor is present in the air. But just like there are only a certain number of books that somebody can hold, that Connor can hold, or that other people can hold, there's also a certain amount of water that the atmosphere can be present in the atmosphere before it becomes saturated. This is what is called saturation vapor pressure. The saturation vapor pressure of the atmosphere is the amount of water vapor necessary for the air to achieve saturation. Let me say that one more time. Saturation vapor pressure, which is different from vapor pressure, saturation vapor pressure is the amount of water vapor needed for the air to be saturated. So vapor pressure is how much water is in the air. Saturation vapor pressure is how much the air can hold. So that is what these two things are. Vapor pressure is simply how much is in the air. Saturation vapor pressure is simply how much the air can hold. What would happen if the two were equal to each other? If vapor pressure was equal to saturation vapor pressure, what would the atmosphere be in that case? Saturated. Yes, thank you, Alan, and thank you, Jerome. Saturated, yes. In that case, the atmosphere would be saturated. And the humidity would be 100%. Now, saturation vapor pressure is highly dependent on air temperature. Going back to that phrase, warm air holds more water vapor than cold air. Now for the more scientific and conscience-clearing version. Warm air has a higher saturation vapor pressure than cold air. So saturation vapor pressure is highly dependent on air temperature. There's one other little fact about saturation vapor pressure that you need to know. It's not going to be very important today, but it's going to be really important next week when we talk about precipitation and we talk about what's called the Bergeron process. And that is, if I have a block of ice and a puddle of water, the saturation vapor pressure is higher over the water than it is over the ice. The reason why this matters is that if the air is saturated and I have an ice cube and a liquid water something, a liquid water puddle or a little cup of liquid water, the air over the ice would condense quicker than it would over the liquid droplet. That allows the ice to grow and the drop to shrink. We'll talk more about that next week. There's usually a nice little activity that I do using M&Ms. Maybe next week for homework, I'll have you all go out and get like a bag of M&Ms or a pack of beads or something if you want to do it that way, to do a little activity. Because yeah, there's actually a cool demonstration that you can do, and I'll actually do it here and show you how to do it. It's really cool stuff. Okay, so saturation vapor pressure is the amount of water vapor needed to saturate the atmosphere. The higher the temperature, the higher the saturation vapor pressure. The higher the temperature, the higher the saturation vapor pressure. And in fact, there's actually a relationship between the two. And there's a whole equation, and there's a curve, and there's a whole thing. There's an equation called the Clausius-Clapeyron equation. It's the relationship between temperature and saturation. It involves using some partial differential equations, a little bit of integration, so some advanced calculus. So you should all be able to do it. I mean, I think that's going to be our next homework assignment. I'm going to have you all derive the Clausius-Clapeyron equation. No, I'm kidding. I would never have you do that. That's like graduate level stuff. What I am going to do, though, is show you the results. So the results are right here, this curve. Can anybody tell me what kind of a curve is this? Anybody know what kind of a curve this is? It's not a perfectly straight, it's something else. Alan. Yes, it is an exponential curve. What that actually means is a small increase of temperature can cause a huge increase in saturation vapor pressure. Now, here's the good news. If you don't know what an exponential curve is, you're totally fine. In fact, I'm not even going to make you use this curve. There's actually a table that I'm going to have you use instead. And I'll actually link to that table in a moment. But basically what the table does is it gives you a temperature, and then 2 columns over, it gives you the saturation vapor pressure. But really what I want you to know right now is that saturation vapor pressure increases with temperature, and saturation vapor pressure for ice is a little bit lower than it is for liquid water. This isn't important now, this will be important next week. And I'll explain why next week. But for right now, the warmer the air, the higher the saturation vapor pressure. I know, who knew humidity could be such a dry topic? There's actually a cool application of this in a moment though. So it does get pretty interesting. Okay. So tying all of this together brings us to the concept of what's called humidity. Humidity is simply an index that describes how much water vapor is in the air. Do me a favor, if you have your phone handy, and even if you're using it for Zoom, you can still do this, open up your weather app. So open up your weather app and look for humidity on it. What unit is humidity provided as? It's provided as a percentage, which means it's a ratio. It's some kind of ratio. That type of humidity is what is called relative humidity. It's actually the most deceitful type of humidity, but it's the one that we use. There are actually several other types of humidity. There is absolute humidity, which is if I take a cubic meter, so roughly 1 meter wide, 1 meter deep, 1 meter tall, and I sucked out all of the water and I weighed it, that would be the mass of that water vapor. That's absolute humidity. On the other hand, if instead of taking a cubic meter, I were to suck out just 1 kilogram of air and weigh the water, that would be called specific humidity. A third type of humidity, if instead of actually weighing the moist air compared to just 1 kilogram, I would instead do what's called a water vapor mixing ratio, which is I would take out that kilogram, weigh the moist air, and then weigh the remaining dry air. And then the ratio between those two is what is called the water vapor mixing ratio. That being said, these 3 types of humidities are only affected by one thing and one thing only: how much water vapor is in the air. How much water vapor is in the air. Relative humidity, on the other hand, the one that you see on the news, is actually a ratio of how much water vapor is in the air to how much water vapor the air can hold. So it's actually a ratio of how much water vapor is in the air compared to how much water vapor the air can hold. So a few minutes ago, I gave you these 2 terms. One of them was for how much water vapor is in the air. The other one is for how much water vapor the air can hold. What were those 2 terms again? Can anybody remind me? What were those 2 terms again? What was the term for how much water vapor is in the air?
Vapor pressure?
Vapor pressure. Meanwhile, what was the term for how much water vapor the air can hold? Saturation vapor pressure. Yes, yes, yes. Well, relative humidity is simply vapor pressure divided by saturation vapor pressure. And then to convert that to a percentage, you would just multiply it by 100. And that would give you some kind of percentage. Now, what determines vapor pressure again? What determines vapor pressure again?
How much water vapor is present in the atmosphere?
How much water vapor is present in the atmosphere? Saturation vapor pressure, that's how much the air can hold. What is that determined by?
The temperature?
Temperature. So, relative humidity actually is affected by two things. It is affected by how much water vapor is in the air and the temperature of the air. In fact, as I'm sitting here right now, I have a little weather station next to me, a little console with weather information on it. When I started class today, the temperature outside was 72 and the relative humidity was 71%. Just since I started class, the temperature is now 76 and the relative humidity is now 65%. The amount of moisture in the air likely hasn't changed. What has changed is the temperature. So let's delve into relative humidity a little bit more. So once again, relative humidity is the ratio of water vapor currently in the air versus the amount needed for saturation at a given temperature and pressure. It is simply the ratio of water vapor's content, how much is in it, to water vapor's capacity. It is simply vapor pressure divided by saturation vapor pressure. It is simply vapor pressure divided by saturation vapor pressure. Let's do something with this real quick. Let's actually do something with this real quick. On the next slide, so just a little bit more about relative humidity. Relative humidity is given as a percent. And what it actually tells us is how saturated the air is. So for a relative humidity of 50%, the air is 50% saturated. For a relative humidity of 25%, the air is 25% saturated. The tricky thing about relative humidity is it's affected by one of two things. Either how much moisture is in the air or the temperature of the air. Those are the two things that affect relative humidity. Those are the two things that affect relative humidity. The amount of moisture in the air or the temperature in the air. And one of those two things happens very often on a daily basis, and that is air temperature. That is air temperature. So here's how it works. let's say I have a situation where the temperature is 20 degrees Celsius and I have a certain amount of water vapor in the air. What would happen to relative humidity if I added more water vapor to the air? Oops. So, what would happen to the relative humidity if I didn't change the temperature, I just added more water vapor? I got one vote for increase. Which of these two things am I affecting? Am I affecting the content or the capacity?
The content.
The content. Yeah, I'm affecting the content. I'm affecting how much is in the air. And that's the numerator here. Well, what happens is when you change a numerator, when you raise a numerator, the overall fraction goes up. Don't believe me? Which one of these two is bigger? Which one of these two is bigger? 1/4 or 2/4? 2/4. Yeah. So by adding more water vapor, I have increased the numerator and I've therefore increased the overall fraction. Therefore, relative humidity increases. Now, on the other hand, let's go back to our initial situation where we had a certain amount of water vapor in the air at a temperature of 20 degrees Celsius. I don't add any more water vapor, but I raise the temperature. Which of these two things have I now affected? Have I affected the content or the capacity? I have a few people telling me that I've affected the capacity. Somebody private messaged me capacity. Well, capacity is the denominator here. If I raise the temperature, I'm raising the capacity. What does that do to the overall fraction if I make the denominator bigger? What does that do to the overall fraction? Oops, somebody else said it, and then I think Kelsey said it too, or what? You got this.
It decreases.
It decreases, yeah. Which one of these two fractions is bigger, 1/2 or 1/3? 1/2 is bigger. The bigger the denominator, the smaller the overall fraction. So what happens is when you raise the temperature, relative humidity goes down. And when you lower the temperature, relative humidity goes up. Let's actually put this to use. Let's do an application now. Based on that concept, as temperature goes up, relative humidity goes down. So as temperature goes up, relative humidity goes down. When should relative humidity be the highest in a 24-hour time period? When should relative humidity be the highest? Why morning? Why morning? Temperature is the lowest. Do you remember? The coldest time of the day is sunrise. So assuming I don't add any water to the atmosphere, relative humidity should be the highest at sunrise. On the other hand, when should relative humidity be the lowest? Why 3 to 5 p.m.? That is when temperature is the highest. Relative humidity is the lowest. Or sorry, whoop, yeah. Scratch that. Sorry. This is a very common mistake that people make. Temperature and relative humidity are inversely related to one another. When temperature goes up, relative humidity goes down. When temperature goes down, relative humidity goes up. They are oppositely related to each other. So if I were to actually draw, I could talk about that in a moment. Great question. Somebody just messaged me. We talked about that real feel or what it feels like temperature. How does relative humidity affect it? I can totally talk about that in a few moments. So if I were to actually draw a graph, I know I said graph. And let's say that this is temperature over here. And this is 12 a.m. Here is noon. And here is 12 a.m. again. At midnight, the temperature should be declining till about 6 a.m. Then the sun comes up, temperature goes up, up, till mid-afternoon. Then it goes back down. How should a relative humidity curve look like on this graph? How should a relative humidity curve look like on this graph? Goes up, then down, then up again, the inverse of the curve. So if I were to actually draw a curve, and just to make sure that I'm demonstrating the proper use of graphing two variables on the same curve, it should look something like this. Relative humidity goes up until temperature reaches its bottom, then it peaks, then it goes down, 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 then it goes back up. Right after temperature peaks, relative humidity dips. And don't worry, I actually do have a graph of this in a few slides. So, but the idea here is that relative humidity is highest when temperature is lowest. And that is why dew forms on the ground in the morning, because that's when it's coldest. Relative humidity is highest, the air is closest to saturation. Now, why does it form on the ground or on blades of grass? Those actually cool a lot quicker than the air does due to radiational cooling. Those cool very quickly. So that's why dew forms on the ground rather than like spontaneously in the air. That happens too. That's called fog. So fog is basically dew in the air. I know, to an extent. So let's do an activity real quickly. Let's do an activity really quickly. I have a QR code right here. If you have your phone, scan this QR code. If you don't have a phone on you right now, give me 1 second and I can, oh, whoops. Sorry, give me 1 second. Let me go back to that slide. There we go. Give me 1 second and I will look this up. And I'll get you the link. Here we go. And here, let me paste this link in chat for those of you who don't have a QR code. So take a moment and pull that up. Take a moment and pull that up, and then we'll talk about it in a second. Okay, give me 1 second here. All right. Sorry, I'm having a tech issue real quickly. Okay. And all right. So I'm about to present you with 3 different scenarios, but first, let me actually show you how to use this table. So let me switch my screen over real quick. Let me copy this real quickly. Let me switch my screen over. Here we go. So this is the table right here that should have pulled up on your phone. Or if you had something else, if you have it in another tab on your browser, or if you have it somewhere else, this is the table that should have pulled up on your phone. Here's how this table works. There are 3 columns, and then the table was split into 2, but there are 3 columns. The column over on the farthest left is the temperature in Fahrenheit. The middle column is the temperature in Celsius. We're going to skip that. And then the column on the right-hand side is the saturation vapor pressure. So, what is the saturation vapor pressure for an air temperature of 55 degrees? What is the saturation vapor pressure for an air temperature of 55 degrees? Fahrenheit. 55 degrees Fahrenheit. Getting lots of responses. Lots of correct responses. So for a temperature of 55, you go over, and a saturation vapor pressure of 14.8. Bingo. Now let's say that the vapor pressure in this case, oops. Let's say that the vapor pressure is 4.3 millibars. What would the relative humidity be if it's 55 degrees outside? What would the relative humidity be if it was 55 degrees outside with a vapor pressure of 4.3 millibars? So relative humidity equals vapor pressure divided by saturation vapor pressure multiplied by 100%. All right, so I've got a vote for 29%. I've got a vote for 29%. Got a second vote for 29%. Well, let's do it. So, vapor pressure is 4.3 millibars. This is actually like almost the most mathy we get in this class. Saturation vapor pressure is 14.8 millibars. That gives us a ratio of 0.29. Converted to a percentage, that's 29%. Bingo. Now let's say the temperature jumps up to 77 degrees. That's what my weather station says right now. What would the relative humidity be in that case? Vapor pressure stays the same, but now the temperature is 77. Oh, I just meant, I gave you that. Somebody asked me, where did I get the 4.3 from? I just gave you that. So that was just a number I pulled out of my head. I will always give you the vapor pressure. Yeah, absolutely. Thank you for asking. Okay, so what would it be if the temperature was 77 degrees Fahrenheit? What would the relative humidity be? All right, I'm getting some messages now. 13.5, 13.6, 14, 13.56. Well, let's do it. So our numerator, the vapor pressure stays the same. That's 4.3 millibars. Saturation vapor pressure is what changes. For 77, saturation vapor pressure is 31.7. Oops. .3 divided by 31.7. 4.3, oops. 4.3 divided by 31.7. 0.1, so 0.156 or 13.56%. I would accept any one of those answers. So 13.5, 13.6, 14. If you round up to the nearest whole percentage, I'm fine with that for relative humidity. So if you round it to the nearest whole percent, that's okay with me. That's okay with me. All right, so now that we've kind of gotten our feet dirty with this, let me actually clear these drawings real quick. If anybody needs to write anything down, are you good? Okay, so that's gone. I'm going to keep this on one side. I'm actually going to share my whole screen now. Because I'm going to end class today with a little in-class activity. This is graded. This is graded. And here it is. Let me share my whole screen now. So here's the activity. Suppose it's a beautiful 70-degree Fahrenheit day and the current vapor pressure is 12.5 millibars. What is the relative humidity? Let me actually I'll answer that question in a second. So let me give you the Google form to submit this at. And then what I'll actually do is then I'll grade this, and you'll be able to see how you did pretty shortly afterwards. let me get this out of the way. Okay. Oh, oh. Okay, so for the first scenario, it's actually right here. So it's a 70-degree day, and the current vapor pressure is 12.5 millibars. What is the relative humidity? I'll even shrink that so that. And then the second scenario, the water vapor content stays the same, but the temperature rises to 85. And then the third scenario, the temperature cools to 60. In all three scenarios, you're using the same vapor pressure. The only thing that changes is the saturation vapor pressure. Okay, let's see here. Oh, oops, sorry. You can just leave it as it is. Yeah, no, you don't have to put in the unit. You can just leave it as it is. If you do put in a unit and it doesn't accept it, just leave it without the unit. All right, let me see how many people have submitted so far, just to kind of get a sense of where people are at. Okay. So it's actually 11:40 right now. So I think what I'm going to do is make this your ticket out the door. So when you're done with this, you are done for the day. Okay, somebody just messaged me. I will get back to them in a second. But once you're done with this, you're done for the day. I do have one announcement to make, and that is our next quiz is next Thursday. It was scheduled for today, but I didn't get the study guide up in time, so I thought rather than making you all wait for that or making you take a quiz without having a study guide, we'll do that next Thursday. All right? So other than that, once you're done, you can sign off as long as you're happy with the answers you've got. You can sign off, and then we'll actually go over them on Tuesday. Have a great weekend, everybody. And I will help out this person really quickly. So yeah, yep, exactly. Exactly. And our next quiz, our next like in-class quiz is next Thursday. And it'll be just like quiz 1.
Thank you, Professor.
Absolutely.
Thank you.
Yeah,
Thank you.
Thank you.
You.
absolutely. Have a great day. You got this. Absolutely.
I have a quick question.
I have a quick answer. How can I help?
So for where it says like for the first one, like how it says 12.5 MB, what does that mean?
Oh, 12.5 millibars. So a unit of pressure is millibars. So vapor pressure is in millibars.
Okay. All right. Thank you.
Yep. I'm hanging around for anybody who has any questions about this or needs any help. Absolutely. Have a great weekend. And I'm still here for the two of you who, okay, for the one of you who's still here. I'm still here if you need my help.
Okay, I just finished. So
Awesome.
sorry, that took a while. I don't know.
No,
I was
not a problem. Not a problem at all.
okay. I don't know. I was struggling on how to read the graph for some reason. I had like some brain fart.
Hey, no, that's okay. That happens. I do it all the time.
Okay, thank you. Have a nice weekend.
You too. All right. Let. Nope, that's that. Let's get out.